Alright, hi Year 11s, this is Mr. Lim here again, and this is another video on chromatography and gases. Today we're learning about high performance liquid chromatography and gas chromatography. Alright, so what are these two things we're going to learn about? They are effectively the newer versions of any chromatographies, and effectively they have superseded all the thin layer and column chromatographies as analytical techniques, and they are used today to do various bits and pieces. Alright, so what is it? Let's go have a look. So in HPLC and gas chromatography, a mixture is then passed through a column packed with stationary phase, just like in other chromatographies. But instead of moving via capillary or gravity, right, they use pressure to push the mixture and the mobile phase through to speed up the process. So it's effectively a bit faster and can do a couple more things. All right, so HPLC pushes the mixture mixed with the liquid mobile phase and pushes it through at high pressure through tubes of the solid stationary phase, whereas gas chromatography first vaporizes the mixture and then mixes it with a gaseous mobile phase and pushes it through a liquid stationary phase coated onto solid particles in a thin column. All right, so over in the top here is your HPLC. You have your mobile phase. It gets pushed through this pump, which puts it under pressure. You inject your sample at this point over here. It goes with the mobile phase through the column, right? And at this point, it will separate, okay? Once it separates out, you're gonna have the various components leave the thing at various times, right? Those things will go through the detector. All right, they'll go through the detector. It'll detect that, hey, that green one came first, that yellow one came second, and then it will come out as waste on the other end, all right? Whereas in the gas chromatography, similar idea. Here's the mobile phase. You push it through under pressure. Again, you have the sample, which comes in right at the last minute. This is inside an oven, so it's nice and hot, so that this sample is vaporized and turned into a gas, mixing with all the other carrier gases. Pushed through this column, right? Out will come one of the substances first before the other substance. This detector will be like, hey, that green one came out first, right? And we'll have some sort of output on the computer, all right? So the idea is that when the components leave the column, so that's that column, that stationary phase, and they're analyzed by different analytical techniques, okay? So that's like your detector. You don't really need to know how it works, but it's effectively being like, boom, something other than the mobile phase is leaving the column, and it will come up with these little pretty spikes to show that something is coming out at those times. All right, so remember, this is all about how to separate the substances, and remember that the things will take different times to go through the columns, and those times are what you're going to be looking at. Okay, so like column chromatography, the components will leave the column at different times based on their interactions with the stationary phase. Okay, so some take longer, some take shorter. The time taken for the component to exit the column is known as retention time, rather than retention factor that we had in the thin layer chromatography. All right, so we can work out qualitative information about the mixtures of the components. Can be worked out by the time taken for the components to leave the column under specific conditions, if these knowns have been previously run under identical conditions. So remember, you have to have the same conditions of your knowns and your unknowns run through so that they come out at ideally the same time, all right, if they are the same component. If you change the conditions, they're not going to come out at the same time. All right, so say for this example over on the right, okay, here's my chromatogram, okay? What it's showing here is that the time in minutes, so 0, 1, 2, 3, 4 minutes, whatever, right? And at this time here, different things came out, and the computer detected that something other than the mobile phase was coming out, all right? Generally here, this line here is where just mobile phase is coming out, right? And so this might not be at 0, actually it might be at like a higher value, but if you see that, why is there like always something coming out? It's the mobile phase. And this, I think, here is just like the computer or the machine doing its thing, starting up or whatever. All right, so you've got 4 clear peaks here where something came out at various times. Which one came out first? It was this one over here because it has the lowest retention time. Which one came out last? This one over here, right? With the highest retention time. Okay, so remember, it's not the one that is the furthest on this side, it's the one that came out first as the lowest retention time, right? So the one that came out first caused this spike here, then this second one that came out caused that spike there, then that one came out later, and then this one came out last, all right? So then if you take some knowns, right, and you run them under identical conditions, the unknowns over here will come out at the same time as your knowns. And so you should be able to work out which one's which. So caffeine here, it's this is supposed to say 3 minutes 56, whatever, or 3 minutes 0.56, like some people use commas instead of things, right? And so you're saying you'll have to work out, okay, well, which one of those peaks is the caffeine, right? And so we say 3.5, so 3.5 is, whoops, come here. The 3.5 is this peak here, right? So that would be what you'd get. You get information about the RT and of a certain component, and you'd be like, which peak is that substance? All right, so benzoic acid is 8 minutes or so, and so that 8 minutes is this peak over here. All right, so that's what we're talking about, saying we can work out which of these peaks is there, and so therefore, if we had something that had like a RT of like 6 minutes, we'd be like, well, that substance isn't in this one here because there is nothing at 6 minutes, right? So if you had a compound, say like ethanol, and it came out at 6 minutes under identical conditions, you'd be like, well, this substance doesn't have any ethanol in it, all right? So on and so forth. All right, so unlike thin layer chromatography and column chromatography, however, now we get into quantitative information about substances can also be gathered via HP, LC, and GC. All right, so let's have a look at how that. Oops. So, as the components leave the column, the detector detects the change in the eluent, which is the substance exiting the column, to indicate a change from the mobile phase. So effectively, mobile phase, mobile phase, mobile phase, mobile phase, mobile phase, like something else, don't worry about that. And then boom, something has come out of the substance there and it's identified as a peak, right? Now, it says here, the higher the concentration of the substance in the eluent, or the higher the concentration of the stuff coming through, the higher the recording from the detector. Okay, so this blue peak compared to this yellow peak, sorry, the green peak and this yellow peak, and I'll make a black peak over here, right? The blue peak has the higher concentration because there's a higher recording from the detector. Okay, so that one there has a higher concentration. It's actually based on the area underneath the curve, right? So you might have something that's like this, all right? And so that area under the curve would probably be much larger than that area under that curve, all right? So that one might have a higher concentration, but that's beside the point, all right? So generally, they're all going to be pretty skinny peaks, and those peaks are going to, the height of the peak will effectively show the concentration of that substance. All right, so as the various components leave the column, they're passing through the detector, can be graphed as a chromatogram showing the times, that's the times, that gives you qualitative information that the components left, and the relative concentration of those components by the size of their peak. So we can say that the blue one at the top here had the highest concentration compared to the green and the yellow and the black, all right? However, what we can't say at the moment is, well, what's that concentration? Is it 1 mole per liter, 2 mole per liter, 3 mole per liter, half a mole per liter, something like that? So right now we still only have qualitative information. We can say that this one has a higher concentration than that one, but we can't say how much. So to get that quantitative information, or to get an absolute concentration, the absolute concentration, to actually say that, okay, that's half a mole per liter, something like that, right? Known concentrations of known components are run through and set conditions to generate a calibration curve to compare unknowns against knowns. Right? I don't know why it's not there. All right, against unknowns against knowns. All right. To generate a calibration curve to compare unknowns against. All right. So what does that mean? So here we have a diagram that shows it. First of all, you prepare a high concentration, medium, less concentration. All right. And so there'll be slowly a lower and lower concentration. Then you run that through, you run those samples through the machine. And so you see here that A1, this one here has to be A1. How does this one here have to be A1? Well, it has the lowest concentration compared to A2, A3, and A4. So A1 would be this one, A2 would be this one, A3 would be this one, A4 would be this one, so on and so forth. Okay, so you run the different concentration samples through the machine, and you'll see that there's lots of different peaks. And since you know that this one here might be 1 mole per liter, this might be 0.75, this might be 0.5, this might be 0.25, you can graph that on a as a calibration curve, where the absorbance or the reading from the detector is plotted on one and the concentration plotted on another. And it seems that this one here is 0.008, 0.006, 0.004, 0.002, so on and so forth. All right, so that was the concentration of these things here plotted against their absorbance, which is these heights here. And then once you have this calibration curve and also a unknown perhaps, so say we have an unknown of unknown reading of say 0.12, right? And so you can see here, let's go zoom in a bit, right? So we have an unknown reading of 0.02, then we can say that, okay, where is 0.12? 0.12 is somewhere here, right? So if 0.12 is somewhere here, then we will draw a horizontal line here, see where it crosses that one there, and say that that one there is approximately 0.004 mole per liter, whatever the concentration is. All right, so calibration curves allow you to work out the concentration of things if you have run the known concentrations through the machine, created this calibration curve, and then run your unknown. Right, so that's quantitative information. You might be given some data, like a table of data showing this stuff here. You would have to plot this out and then use it to work out the thing. So, you know, they would give this information to you, like the concentration as well as the absorbance in like a table or something, and then ask you to graph it and then ask you to use an unknown to work out its concentration. Right. Some other questions that you might get are like, you know, just thinking about how to use this as a chromatography thing where you have to work out which one's polar, which one's non-polar. So here we have a gas chromatogram with a stationary phase as polar and a mobile phase as non-polar. Okay, so stationary phase polar, mobile phase non-polar, which is the most polar substance. Okay, so if the stationary phase is polar, things that are polar will stay with the stationary phase and interact with it a lot, which will means that things that are polar will spend a lot of time in the column in the stationary phase, which means that they'll have a high or low RT. They'll have a high RT. So things that are polar will have a high RT. Okay, and things that are non-polar will have a low RT. So then, which is the most polar substance? Which one is the highest RT? That this one here. This is the most polar. Okay. Which of the substances has the lowest concentration? All right. So remember, the lowest concentration is the lowest peak, and C, since these all have the same width, therefore C probably has the lowest concentration. Assuming all of these are hydrocarbons, which is the largest. Okay, so remember, hydrocarbons are generally non-polar, but they still have varying degrees of polarity. All right, the largest one will be the most non-polar, and therefore, since the largest one that is the most non-polar, which one is the largest, will probably be A, because it is the one that was the lowest RT. No, wait. Yes, because the mobile is spending the most time in the mobile phase and therefore going through the system the fastest. All right, which substance is benzene with an RT of 13.5? Okay, so 13.5, you would find that over here, which is around about here-ish, okay, which means that that substance is C, that's benzene there. All right, so that's an example of some types of questions. That's it. Adios.